We'll begin here talking about the real numbers and different subsets within the real numbers. In this class, we're only going to focus on real numbers. There are a different group of numbers called imaginary numbers, but for us, let's just realize that every number we're going to see is a real number. Now, real numbers can be split into other categories. The real numbers can be split into the rational numbers and the irrational numbers. Now, within the rational numbers, we can separate them more and more. Rational numbers, we know integers are rational numbers, so the integers are a smaller set within the rational numbers because every integer is a rational number, but we know from our previous study that not every rational number is an integer. So that's why they're a smaller set. Now, the integers contain both the positive and negative values, but if we were to look at only the non-negative integers, 0, 1, 2, 3, 4, that's what would be called whole numbers. So within the integers, we've got a smaller set of whole numbers. And within that, we say, what if we were only considering the positive ones? 1, 2, 3, 4, so notice we get rid of the 0. That's what we would call the natural numbers. So we can split it to an even smaller set that is just called the natural numbers. So the real numbers can be separated into these categories. One thing we want to keep in mind is this embedded nature. Every natural number is a whole number. Every whole number is an integer. Every integer is a rational number. Every rational number is a real number. But the reverse of that is not true. Notice every rational number is not an integer because there's rational numbers that are not integers. That's why the integers live inside of the rational numbers. So we have this in mind. These are our important types of real numbers. We've got these categories. And whenever you're thinking of an irrational number, you would just think of a number that is not rational. And for our class, one of our basic irrational numbers is the square root of 2 is irrational, but the square root of 4 is rational because if we type square root of 4 into our calculator, we would actually get that the square root of 4 is really the value 2. So even though it looks complicated, the square root of 4 is just hiding the integer 2, and we know integers are rational numbers. So for this class, how are you going to recognize irrational numbers? It's going to be whenever it's the square root of a number that can't be simplified further. So the square root of 4 is a rational number because it can be simplified further to be 2, but the square root of 2 can't be simplified any further. And we're not going to focus too much on this in this lesson. So let's consider, is it possible to have a number that is a natural number and that number would also be considered a whole number? So let's look back at our description. We know that to be a natural number, you have to be one of these, so the positive integers. So we are a positive integer, and we ask ourselves, are we guaranteed that every positive integer also lives in this classification? And I would say yes, every natural number is a whole number. It's just that not every whole number is a natural number. For instance, we see that 0 is a whole number, but not a natural number. But in this case, it is true that every natural number is a whole number. So we could say yes, and our example is maybe 1 is a natural number and a whole number. Is it possible to have an integer? So here we're starting with an integer that is not a natural number. So we're in the integers, but it's not a natural number. So let's look, where are we starting? We are starting with the integers, so we're one of these. Is it possible to be one of these and not one of these? That is not possible, right? Because every integer, oh, actually it is possible, sorry about that. Although all of these integers map to the natural numbers, do we see any negative integer or integer that's 0 does not belong in the natural number set? So any of the integers 0, -1, -2, -3, while integers are not in the natural numbers, because the natural numbers start at +1 and continue forward. So here we would have that this is possible, and any of our examples could be any of the negative numbers or zeros, so we could say like maybe -2 is an integer, but not a natural number. Next we're asked, is it possible to be both rational and irrational at the same time? And this is not possible. By definition, irrational numbers are the numbers that are not rational. So we would say no. By definition, irrational numbers are not rational. If we go back to our chart, this can be more evident. Notice here are the rational numbers, here are the irrational numbers, and see that there's no overlap. They can have nothing in common. They are completely separate entities. So one type of example that we might see is we'll be given a list of numbers, and we want to match them into every category that they belong. So for instance, in our class, we know every number is a real number. So we're just going to first copy down the set in the category of real numbers. And then once we get that written in the real numbers, we can break things down further if necessary. So let's begin with the largest set. Every number in our class is a real number, so we get the real numbers are -5, -1/3, 0, square root of 2, 11/4, 4, and 5.422. And if we look at our categories from before on our first page, all we've showed now is that everything is a real number. From that, it gets broken down into smaller categories of, is it rational or irrational? Once you know what the rational numbers are, we can break it down further. Is it an integer, a whole number, or a natural number? So that's the progression we're going to follow in this example. Looking at our list of real numbers, the only irrational number we see is the square root of 2. It is the irrational number. It's the irreducible square root. So that goes here. But then all the other numbers, except for that, are the rational numbers, because by definition the rationals are everything that is not irrational. So all the other digits get split into the rational number category. Let's write that down. But within the category of rational numbers, we can split them even farther into the things that are integers, the things that are whole numbers, and the things that are natural numbers. So the next largest category is integers, and that's all of our values here. And one thing to note before we write down the integers, remember rational numbers are numbers that can be expressed as fraction of integers, and we might say, well, how can this be expressed as a fraction of integers? This is equal to 5,422 divided by 1,000. You can type this into your calculator and verify. And the way that I determined that is I found the decimal place. I had to move over 3 places. That's where I got the 5,422. And since I moved over 3 places, I divided by 1,000. I added 3 zeros after the 1. So although this decimal doesn't look like a rational number, it actually can be expressed as a rational number. Similarly, we know we could write 4 is 4 divided by 1, 0 is 0 divided by 1, -5 is -5 divided by 1. So all of these are rational numbers. Now the integers are particularly -5, 0, and 4. All of these would go with our integer list. -1/3 is not an integer, nor is 11/4, nor is 5.422. Now the whole numbers are the non-negative integers, so that would include 0 and 4. Those are our whole numbers. But the natural numbers don't include 0. It's only the positive integers, so that would be 4. And just by this method, we started with the largest category, and then we split it into the 2 next categories. Once we did that, we split it into our final 3 smallest categories. And we have shown where each of these numbers reside, and notice some numbers fit multiple categories. That's because of the embedded nature of our diagram. Every natural number is a whole number, every whole number is an integer, every integer is a rational number, every rational number is a real number. Next, we're going to talk about some different properties that hold within the addition and multiplication of real numbers. But before we go to that, I want to first show us some sets of numbers where these categories don't hold. That way we can have a better understanding of why they work in the real numbers and why they're important. So let's first take a small aside. Let's consider the set of negative integers. Now, whenever we think about this, if we wanted to remain in the set of negative integers, we would ask ourselves, could I multiply any two items in the negative integers, let's say negative 4 times negative 2. Notice negative times negative makes it positive, so we'd actually get to 8, which is not a negative integer. So if we were working with this and we wanted to only look at mathematical operations that keep us inside the set, we would say that multiplication is not closed for the set of negative integers. The reason I would say that multiplication is keyword not closed is because we could take something that is a negative integer and multiply it by another negative integer, but we get something that is not a negative integer. So whenever we later talk about the property of an operation, add, multiply, subtract, or divide being closed, what that means is if you start in the group and you perform the operation with something else in the group, you should stay in the group. And if you don't stay in the group, that's the idea of it not being closed. Now think about our negative integers and think about the mathematical operations add, multiply, subtract, divide. We already saw that multiplication is not closed. Let's think about whether addition is closed for the negative integers. So it's always a specific operation, a specific set that you're looking at, and then you decide whether it's closed or not. So now our operation is addition, and we want to know for the negative integers whether it would be closed or not. So we would just consider some different examples. Let's take negative 4 and add that to negative 3. Negative plus negative stays negative, so we would say that addition is closed, because if you keep a negative integer and you add it to another negative integer, you stay a negative integer. So addition is closed. I know this is a little new, but try to keep in mind something's closed if something from the group with that mathematical operation and something else from the group stays in the group. So why don't you take a moment to consider whether subtraction is closed or not closed for the negative integers. So to do so, you would pick a negative integer, 2 of them, subtract them, and see if they stay negative integers. And I would think about picking a few. So why don't we take a moment to pause the video, work on a few such examples. When you think you have an idea, unpause to check your work. So if I first pick negative 3 minus negative 1, these are both negative integers that I'm subtracting. Now minus a negative is actually the same thing as a positive, so it's like we're taking negative 3 and effectively adding 1. So at that case it stays negative, but we would need to think through a few more options, because what if instead I had taken the negative 1 and subtracted that from the negative 3? Because you subtract a negative turns it into a positive, the thing is, if the second number that we're subtracting is a larger negative than the first, whenever we turn to adding it, that's actually going to make us positive. So notice in the first case, negative minus negative, negative minus negative kept us negative. But there's other cases we construct where negative minus negative makes us positive. In this case, if the second number that's negative is more further negative, then when we minus the negative and make it a positive, this positive 3 is going to counterbalance the negative 1 and actually turn us into a positive number. So for that reason, subtraction is also not closed for the negative integers. Now take a moment to think about whether division would be closed or not closed. I recommend you pause, look at a few examples, make a conclusion, and then check your work. Now if I pick any two negative numbers, let's say -2 and divide that by -1, negative divided by negative is positive. So notice we could take a negative integer, use the operation division with another negative integer, and we leave the negative integers. So for that reason, division is also not closed. Now, if we're dealing with sets of numbers and operations, we would want to only deal with sets of numbers that are large enough and operations that are well behaved enough that if we perform the mathematical operations, they are closed, because we want to be able to, wherever we started, end up in that same place. And that's why we like to often look at the real numbers, because in the real numbers, they are closed under addition, subtraction, multiplication, and division, and we just saw a circumstance where you could think of a certain set where that's not guaranteed. So let's introduce some of these properties that are related to real numbers. We already discussed the idea of closure properties. For instance, we looked at the negative integers where they were closed under addition but not under anything else. But if we expand our view out to the real numbers, our largest category of numbers that we're looking at, then the real numbers happen to be closed. What that means is if we start with a real number and we add a real number to it, then the result is going to still be a real number. And the same works for multiplication. Real number times real number together is a real number. Now, another property that we haven't talked about yet is the commutative property. And it's behind the phrase, if you've ever seen 2 plus 3, that's why you can write it as 3 plus 2. You might have heard in the real number system, order of addition does not matter. Same thing for multiplication. 2 times 3 is the same as 3 times 2. That's the name for the commutative property. And I like to just think about this as the order of addition does not matter, nor does the order of multiplication. Now, the next property is the associative property, and that comes whenever you've got a string of addition or multiplication. For instance, if we had 3 plus 2 plus 5, all the associative property is since you're adding, only adding, it doesn't matter whether you add these first and then add the 5, or if you add the 2 and the 5 first and then add the 3, which is expressed by this. Remember, the parentheses say do this first, so all this is saying is if you're adding a group of numbers, it does not matter the order that you add them. So 3 plus 2 and then plus 5 is the same as 2 plus 5 and then plus 3. The key is we're adding all the same things, and that's expressed by this. Notice the parentheses switch who gets added first, and this is the same for multiplication. A times B then times C is the same as A times B times C first. That's called the associative property. Now next we have the idea of the identity property. The identity property is that under the operations of addition and multiplication, we should be able to add a number and multiply by a particular number, and it's not going to change the expression. Now you think about it. 3 plus what number would keep us at 3? What number, when you add it, doesn't change your position? That would be 0. So 0 is what's called the additive identity, because if you add it to any number, you stay at your starting number. For multiplication, we would think 3 times what keeps me at 3? What number can you multiply by any number but still stay at that number? That would be 1. So 1 is the multiplicative identity because 3 times 1 keeps us at 3. So within addition and multiplication, we've got two different identities. A plus 0 keeps you at A, and then A times 1 keeps you at A. So in the first case, 0 is the additive identity, and 1 is the multiplicative identity. Now inverses are somewhat related. It's the idea that if you started a number, you should be able to get back to the identity number. So for instance, if we start at 3, 3 plus what would get us back to the identity of 0 for addition? That would be -3. And if we had started at 3, 3 times what gets us back to the identity of 1 for multiplication. In this case, that would be 1/3. So in this case, we have both additive identities, because we can get back to the additive identity, and multiplicative inverses, because we can get back to the multiplicative identity in the real number system. So we would express that as, for real numbers, if you start at a, you could add negative a, and you get back to the additive identity. And for multiplication, if you start with the number a, then if you multiply by 1 divided by that a, notice we started with 3, we multiply by 1 divided by 3, that's going to get you back to the multiplicative identity of 1. Now finally, the distributive property just has us think about what happens if we want to mix these operations. Notice here, first you add b plus c and then you multiply by a. That's the idea of maybe saying 3 times 2 plus 5. Well, you could add these together and then multiply, or you could multiply them separately and then add the results. So that's saying you could distribute the multiplication across addition, and that's expressed as a times b plus c is the same as multiplying a times the first term and then just adding that result of a times the second term. So these are our main properties: closure, commutative, associative, identity, inverse, and distributive. And the way we're going to see this in our class is we're going to be given a statement and we need to identify what property is this illustrating. So let's look at our first example. And if you have this with you in your notes, just keep this page handy as I turn the page. It will help if you can look at this. So for our first example, it makes the statement 3 plus 9 is a real number. Now let me break this down for us. 3 is a real number, 9 is a real number, and when you add them, you stay that same type of number. Which of our earlier examples does that match? You're at a real number, you add a real number, and you stay a real number. That would be the closure property, the idea of if you're in the group, you stay in the group if you do that operation. Next, we'll look at the statement 9 plus 0 equals 9, and then we think through what is this trying to tell us. And then we see that would be the identity property, the idea that you can start at a number, add 0 to it, and then stay at the number. That's our 9 plus 0 equals 9, so this illustrates the identity property. Now take a moment to take special care and look at these next two. I would say they look similar in that there's two addition symbols and parentheses, but there's a key difference. So look at these two and think, which two properties do they illustrate? I recommend you pause the video, determine it, and then unpause to check your work. Now here in the first one, we notice the key detail is that inside the parentheses there's the 9 and the 3 in the first one, and the 9 and the 3 in the second one, but do we see the order of addition is switched? At first it was 3 plus 9, and then it was 9 plus 3. So this statement is telling us that order of addition does not matter, which is the idea of the commutative property. Whereas the other one is different because notice it regroups. At first we were adding the 6 and the 8 and then adding the 5. But on the right side, now we're adding the 5 and the 6 first and then adding the 8. And we're saying that that would still be equal. That's the idea of the associative property. Now our last statement has one number times another number equals 1. And we remember 1 is the multiplicative identity. So if you've got a number and you can multiply it by another number and then get back to the identity 1, that's the inverse property, specifically multiplicative inverse. So this shows the idea that we've got an inverse. So for this section, we just want to be able to look at a statement and then understand which of the properties from here it's representing: closure, commutative, associative, identity, inverse, or distributive. And here we have our homework as before. Remember, they're odd, so you can check your answer in the back of the book. Seek help if you get a problem incorrect, and that way you can prepare before you take our section quiz over 5.5.